Close your eyes and let yourself sink deeper into comfort. Feel the softness beneath you, the gentle weight of your blankets, the quiet stillness of the room around you. Tonight, we're going to drift together through the most peaceful corners of the cosmos, exploring the gentle majesty of galaxies that spin silently through the infinite dark. There's no rush, nowhere to be. Just you, this moment, and the soothing vastness of space stretching endlessly in all directions. Let each word wash over you like a slow, cosmic tide. Let your breathing slow to match the ancient rhythms of the universe itself. We have all the time in the world, or rather, all the time in 13.8 billion years of cosmic history. So settle in. Release the tension from your shoulders, your jaw, your hands, and let's begin our journey into the most serene facts about galaxies that the universe has to offer. The cosmic scale, understanding our place. When we think about the universe, it helps to start with something both humbling and oddly comforting: the sheer vastness of space itself. The distances involved in astronomy are so enormous that they require their own unit of measurement, something beyond miles or kilometers, beyond anything we experience in our daily lives. This is where the light year comes in, and understanding it is like finding a key that unlocks the door to cosmic comprehension. A light year is not a measure of time, despite its name. It's a measure of distance, specifically the distance that light travels in one full Earth year. And light moves fast, remarkably, impossibly fast. In a single second, light travels 186,000 miles. In that same second, a beam of light could circle the Earth's equator more than 7 times. It's a speed so tremendous that nothing in the universe can move faster. And yet, even at this incredible velocity, it takes light an entire year to cover what we call 1 light year of distance. To put this in perspective, imagine you could travel at the speed of light. You could reach the moon in just over a second. You could zip from Earth to Mars in about 3 minutes, depending on where the planets are in their orbits. You could travel from the Sun to the outermost reaches of our solar system, out past Neptune and Pluto in just a few hours. But to cross the distance of a single light year would take you an entire year of continuous travel at light speed. This is the cosmic ruler by which we measure the distance between stars and galaxies. Our closest stellar neighbor beyond the Sun is Proxima Centauri, a small red dwarf star that sits about 4.2 light-years away from us. That means when we look at Proxima Centauri in the night sky, we're seeing light that left that star over 4 years ago. We're looking back in time, seeing the star not as it is now, but as it was when that light began its journey across the void. This time delay becomes more and more pronounced as we look at objects farther and farther away, until we reach the most distant galaxies, where we're observing light that has been traveling through space for more than 13 billion years, light that left those galaxies when the universe itself was young and strange. The Milky Way galaxy, our home in the cosmos, stretches approximately 100,000 light-years from edge to edge. Try to let that sink in for a moment. If you could somehow board a spacecraft and travel at the speed of light, starting from one side of our galaxy and heading straight across to the other side, it would take you 100,000 years to complete the journey. Entire civilizations could rise and fall during that crossing. Human history as we know it, from the first stone tools to modern civilization, spans only a few 100,000 years. The width of our galaxy dwarfs the entire story of humanity. And the Milky Way is just one galaxy among hundreds of billions, perhaps even trillions, scattered throughout the observable universe. The observable universe itself, the portion of the cosmos from which light has had time to reach us since the Big Bang, extends approximately 93 billion light-years across. This is larger than you might expect from a universe that's 13.8 billion years old, and the reason has to do with the expansion of space itself. Space has been stretching and growing during the entire time that light has been traveling toward us from distant galaxies, effectively increasing the distance between us and those ancient light sources. Think about your cosmic address for a moment. You live on Earth, a planet orbiting the Sun. The Sun is one star among roughly 200 billion stars in the Milky Way galaxy. The Milky Way is part of the Local Group, a collection of more than 50 galaxies spanning several million light-years. The Local Group itself sits on the outer fringes of the Virgo supercluster, and even that enormous structure is just one part of the Laniakea supercluster, which contains approximately 100,000 galaxies spread across 520 million light-years of space. And Laniakea is merely one supercluster among countless others throughout the observable universe. These distances are so vast that they become almost abstract, numbers too large to truly comprehend. But there's something deeply peaceful about this perspective. All of our daily worries, our anxieties, our struggles, they all take place on a tiny blue marble orbiting an ordinary star in an unremarkable section of a galaxy that is itself just one among billions. From the cosmic perspective, everything that has ever troubled you is happening in an almost infinitesimally small corner of a vast and ancient universe. This isn't meant to diminish the importance of our lives, but rather to offer a different kind of comfort. We are part of something unimaginably large, something that has been unfolding for billions of years and will continue for billions more. We are temporary patterns in an eternal dance of matter and energy. The light from distant galaxies has been traveling for so long that it carries with it information about the universe as it was in the deep past. When we look at a galaxy that is 10 billion light-years away, we're seeing that galaxy as it appeared 10 billion years ago, when the universe was less than a quarter of its current age. We're essentially looking back through time, watching the story of cosmic evolution unfold. Every distant galaxy is a window into history, a frozen moment from an era when the cosmos was younger, stranger, and more chaotic than it is today. What makes this even more interesting is that because the universe is expanding, these galaxies are moving away from us. The space between our galaxy and distant galaxies is stretching, carrying those faraway islands of stars ever further from our view. Galaxies that are very far away are receding from us at significant fractions of the speed of light, not because they're physically moving through space that quickly, but because the space between us and them is expanding. This is why, when astronomers measure the light from distant galaxies, they find that it has been shifted toward the red end of the spectrum, a phenomenon called redshift. The wavelengths of light have been stretched by the expansion of space during the light's long journey to reach our telescopes. There's a horizon to what we can see, a cosmic event horizon beyond which we cannot observe because light from those regions hasn't had enough time to reach us yet since the Big Bang. This observable universe, as vast as it is, might be just a tiny fraction of the full universe. There could be galaxies beyond our horizon that we will never see, entire cosmic archipelagos forever hidden from our view by the simple fact that their light hasn't had time to cross the immense distance to reach us. Some of those galaxies are receding so quickly due to the expansion of space that their light will never reach us, no matter how long we wait. All of this context helps us understand just how special and rare our view of the cosmos truly is. We exist at a time when the universe is old enough for complex structures like galaxies to have formed, but still young enough that we can see those structures scattered across the cosmic landscape. In the far future, trillions of years from now, the continued expansion of space will have carried distant galaxies so far away that future astronomers, if any exist, will see a much emptier universe than we do. The rich tapestry of galaxies that fills our telescopes today will have receded beyond the horizon of observability. We are living in a cosmically special time, a golden age of visibility when the history of the universe is written in light across the sky for those patient and curious enough to read it. The Milky Way, our galactic home. Let's turn our attention now to our home galaxy, the Milky Way, and explore it with the gentle curiosity of someone discovering a familiar place for the first time. The name itself is ancient, coming from the Greek word galaxias, meaning milky, which describes exactly how our galaxy appears when viewed from Earth on a dark, clear night. That misty band of light stretching across the sky is actually our view of the galactic disk from inside it, billions of stars so distant that they blur together into a luminous river flowing across the darkness. The Milky Way is a barred spiral galaxy, which means it has a particular structure and form that we can describe even though we've never seen it from the outside. Imagine looking down on our galaxy from high above, from a vantage point millions of light years away. What you would see is a beautiful spiral structure, like water swirling down a cosmic drain, but frozen and majestic and impossibly vast. At the center would be a bright, elongated bulge of older yellowish stars, with two major spiral arms wrapping around it, each arm studded with brilliant blue regions where young, hot stars are being born even now. These spiral arms, known as the Scutum Centaurus arm and the Perseus arm, are the most prominent features of our galaxy's disk. They contain the highest concentrations of stars, both young and old, and they're where most of the galaxy's star formation activity takes place. There are also less prominent features called minor arms, including the Norma arm and the Sagittarius arm, which contain primarily gas and pockets of star-forming activity. Our own solar system sits in what's called the Orion spur or Orion arm, which is actually a minor feature connecting the Perseus and Sagittarius arms. We live, in other words, in a cosmic suburb out in the quieter regions between the major spiral arms. The disk of the Milky Way extends roughly 100,000 light-years from edge to edge, but it's remarkably thin compared to its width. The disk is only about 1,000 light-years thick in most places, giving the galaxy a shape somewhat like two fried eggs placed back to back, with the yolks meeting in the middle to form the central bulge. This flat, spinning disk contains most of the galaxy's visible matter, including stars, gas clouds, and dust, all orbiting around the galactic center in a great cosmic carousel that has been turning for more than 13 billion years. The structure of the Milky Way can be thought of as having several distinct components that blend into each other. At the very center, occupying a tiny region only about 400 light-years across, is the nucleus. This is an extreme environment containing a supermassive black hole called Sagittarius A star, which has a mass equivalent to roughly 4 million times the mass of our Sun. Despite its enormous mass, this black hole isn't going to swallow the galaxy. Our solar system orbits at a comfortable distance of about 26,000 light-years from the galactic center, far beyond the black hole's immediate gravitational influence. Surrounding the nucleus is the central bulge, a dense swarm of stars roughly 10,000 light-years across. This bulge is composed primarily of older, reddish stars, giving the center of our galaxy a yellowish-orange glow when viewed in visible light. These are stars that formed billions of years ago from the original clouds of gas that coalesced to create our galaxy. They've been orbiting the galactic center ever since, slowly converting their hydrogen fuel into heavier elements, gradually dimming as they age. The outer parts of the bulge are difficult to distinguish from the inner parts of what astronomers call the galactic halo, a roughly spherical region that surrounds the entire galaxy. The disk itself comes in two varieties, a thin disk and a thick disk. The thin disk contains the youngest stars, the gas, and the dust, materials that are concentrated into the spiral arms where ongoing star formation continues to light up the galaxy with the bright blue-white glow of massive, short-lived stars. The thick disk contains somewhat older stars and extends farther above and below the galactic plane. These stellar populations represent different generations of star formation, snapshots of different eras in our galaxy's long history. The spiral arms themselves are fascinating features. For many years, astronomers weren't entirely sure our galaxy even had spiral arms, because observing the structure of the Milky Way from inside it is extremely difficult, like trying to determine the shape of a forest while standing among the trees. Much of our understanding of the Milky Way's spiral structure comes from observations of neutral hydrogen and molecular clouds, which can be detected through the dust that obscures optical light. These observations, combined with careful studies of the distances to stellar associations and star-forming regions, have allowed astronomers to map out the spiral pattern. The spiral arms are not permanent structures in the way you might imagine. They're more like density waves moving through the disk, regions where stars and gas are temporarily concentrated as they orbit the galactic center. Think of traffic on a highway. Sometimes cars bunch up into slow-moving groups, creating a region of higher density that moves along the road. Individual cars enter the traffic jam from behind, slow down as they pass through it, and then speed up again as they exit the front of the congestion. The traffic jam itself moves along the highway, even though it's always made up of different cars. Similarly, the spiral arms are regions of higher density that persist over time, even though individual stars and clouds move in and out of them during their orbits around the galaxy. The process of stars entering and leaving spiral arms has important consequences for star formation. When gas clouds enter a spiral arm, they experience increased density and gravitational pressure, which can trigger the collapse of clouds and the formation of new stars. This is why spiral arms appear bright and bluish in photographs. They're lined with recently formed, massive stars that burn hot and blue. These young stellar giants live fast and die young, often exploding as supernovae before they can drift too far from their birthplace in the spiral arm. This means that spiral arms are simultaneously regions of birth and death, places where the cycle of stellar life turns most vigorously. Our Sun, along with the entire solar system, is orbiting the center of the Milky Way at a speed of about 225 kilometers per second. At this velocity, it takes approximately 240 million years for us to complete one full orbit around the galaxy. This period is sometimes called a cosmic year or a galactic year. The last time our solar system was at its current position in its orbit around the galaxy, dinosaurs were just beginning to evolve on Earth. Since the Sun formed about 4.6 billion years ago, it has completed roughly 18 to 20 orbits around the Milky Way. We're currently traveling through the Orion Arm, on a path that will eventually carry us through different parts of the galactic disk over hundreds of millions of years. The Milky Way isn't alone in space. It's accompanied by numerous smaller satellite galaxies, dwarf galaxies that orbit around it much like moons orbit a planet. The most famous of these satellites are the Large and Small Magellanic Clouds, irregular dwarf galaxies visible from Earth's southern hemisphere. These companions are being slowly pulled apart by the Milky Way's gravity, with streams of gas and stars being stripped away and drawn into our galaxy. This process, called tidal stripping, is one way that large galaxies like the Milky Way grow over time, gradually consuming smaller neighbors that venture too close. Throughout its lifetime, the Milky Way has undergone many such mergers and interactions. Astronomers can detect the remnants of past collisions by studying the motion and chemistry of stars in the galactic halo. Some stars move in unusual orbits or have chemical compositions that don't match what we'd expect if they had formed within the Milky Way. These stars are likely the survivors of dwarf galaxies that merged with our galaxy in the distant past, their original homes long since torn apart and absorbed into the Milky Way's structure. The stars in our galaxy come in different populations that reflect different eras of galactic history. Population 1 stars, which include our Sun, are relatively young and metal-rich. In astronomical terms, metals are any elements heavier than hydrogen and helium, and these elements are produced inside stars through nuclear fusion and then distributed into space when stars die, either through gentle stellar winds or violent supernova explosions. Population 1 stars formed from gas clouds that were already enriched with metals from previous generations of stars. Population 2 stars, on the other hand, are older and metal-poor. They formed earlier in the galaxy's history when there had been fewer stellar generations to produce and distribute heavy elements. These ancient stars are found primarily in the galactic halo and in globular clusters, dense balls of hundreds of thousands of stars that orbit the Milky Way. The Milky Way is estimated to contain between 200 billion and 400 billion stars, though the exact count is uncertain and depends on assumptions about the number of small, dim stars that are difficult to detect. Alongside these stars are perhaps 100 billion planets or more, many of which orbit in the habitable zones around their stars where liquid water could exist on planetary surfaces. The sheer number of potentially habitable worlds in our galaxy alone suggests that we're unlikely to be alone in the universe, though whether intelligent life is common or vanishingly rare remains one of the great unanswered questions of our time. Looking at the Milky Way galaxy from our position within it instills a particular kind of wonder. We are part of this vast, ancient, slowly rotating system, a tiny component of something incomprehensibly larger than ourselves. Every star you can see with your naked eye at night is part of our galaxy, fellow travelers on this same cosmic journey. The stars we see aren't arranged randomly. They form the local neighborhood of our galactic suburb, stars within a few hundred light-years of the Sun. Beyond them, invisible to the naked eye but detected by our telescopes, lie billions more stars extending in every direction. A three-dimensional sea of suns reaching out to the galaxy's edge. Neighboring galaxies and the local group. As vast as the Milky Way is, it's not alone in the cosmos. Our galaxy exists as part of a community of galaxies, bound together by mutual gravitational attraction, slowly dancing through space in a gravitational ballet that has been unfolding for billions of years. This community is called the local group, and understanding it helps us see how galaxies organize themselves on scales larger than individual galaxies but smaller than the great superclusters that make up the largest structures in the universe. The local group spans approximately 10 million light-years across and contains more than 50 galaxies, though the exact number keeps changing as astronomers discover new, extremely faint dwarf galaxies that had previously escaped detection. Most of these galaxies are small, containing only millions or tens of millions of stars, making them dim and difficult to find against the backdrop of more distant galaxies. But within this group of dozens of galaxies, 3 stand out as giants: the Andromeda Galaxy, the Milky Way, and the Triangulum Galaxy. The Andromeda Galaxy, also known as Messier 31 or simply M31, is the largest member of the local group and our closest major galactic neighbor. It lies approximately 2.5 million light-years away from us, a distance that seems immense until you remember that this is actually quite close on cosmic scales. Andromeda is a barred spiral galaxy much like our own Milky Way, containing perhaps 1 trillion stars compared to the Milky Way's few hundred billion. When you look at Andromeda through a telescope, you're seeing a galaxy that might be very similar to what the Milky Way would look like if you could view it from outside. On a very dark, clear night, far from city lights, you can actually see the Andromeda Galaxy with your naked eye. It appears as a faint, fuzzy patch of light in the constellation Andromeda, and what you're seeing is the combined light of 1 trillion suns, light that has been traveling through space for 2.5 million years before reaching your eyes. When that light left Andromeda, early humans were just beginning to use primitive stone tools on the plains of Africa. The light you see tonight shows you what Andromeda looked like in that ancient time, not as it appears right now. Andromeda's disk spans approximately 150,000 light-years across, making it larger in diameter than the Milky Way, though recent studies suggest the 2 galaxies may have similar total masses when you account for all their stars, gas, and dark matter. Like the Milky Way, Andromeda has its own collection of satellite galaxies, including 2 that are easily visible in amateur telescopes: Messier 32 and NGC 205, both small elliptical galaxies that orbit their massive companion. The interesting and slightly unsettling fact about Andromeda is that it's not simply sitting peacefully in space. It's moving toward us. Measurements of Andromeda's spectrum reveal a blue shift, meaning the wavelengths of its light are compressed rather than stretched, indicating motion toward rather than away from us. The galaxy is approaching at approximately 300 kilometers per second. This makes Andromeda one of only about 100 galaxies in the observable universe that are moving toward us rather than away. Virtually everything else is receding due to the expansion of space, but Andromeda is close enough that its own motion and the Milky Way's gravity overcome that expansion. In approximately 4 billion years, give or take a billion, the Milky Way and Andromeda will collide. This sounds dramatic, and in cosmic terms it is, but it's worth understanding what will actually happen during this collision. The 2 galaxies will approach each other, drawn together by mutual gravity. As they get closer, their gravitational interaction will distort their shapes, pulling out long tidal tails of stars and gas. The galaxies will pass through each other. Remember, galaxies are mostly empty space, so even though the galaxies collide, individual stars almost never hit each other directly. The stars will be gravitationally jostled and flung into new orbits, but they won't physically crash together. After the first pass, the galaxies will swing around and fall back toward each other for a second collision, and possibly a third. Over the course of several billion years, the two spirals will merge into a single, larger galaxy. Most astronomers expect the result to be a giant elliptical galaxy, a ball-shaped swarm of stars with no remaining spiral structure. This combined galaxy has already been given a nickname by some astronomers: Milkomeda, a blend of Milky Way and Andromeda. By the time this merger is complete, the Sun will likely have already swelled into a red giant and consumed the inner planets, so humanity, if it still exists, will have long since needed to find a new home among the stars. The third major galaxy in the local group is the Triangulum Galaxy, also known as Messier 33 or M33. It's smaller than both the Milky Way and Andromeda, containing perhaps 40 billion stars and spanning roughly 60,000 light-years in diameter. Triangulum is a beautiful spiral galaxy when viewed face-on, and it's the most distant object that can potentially be seen with the naked eye under absolutely ideal conditions, though most people need binoculars or a small telescope to spot it. The galaxy lies about 3 million light-years away, slightly farther than Andromeda. There's some debate about whether Triangulum is actually orbiting Andromeda or if it's an independent member of the local group. Some evidence suggests the two galaxies had a close encounter 2 to 4 billion years ago, which triggered a burst of star formation in Andromeda's disk. If this is true, then Triangulum's gravity helped shape Andromeda into its current form. The future relationship between these galaxies remains uncertain. Triangulum might eventually merge with Andromeda, or it might be pulled into the future collision between Andromeda and the Milky Way, making it a three-way merger instead of a two-way collision. Beyond these three giants, the local group contains numerous smaller galaxies. Many of them are dwarf spheroidal galaxies, small collections of stars that have very little gas or dust remaining and have long since stopped forming new stars. These are some of the faintest galaxies in the universe, and they're incredibly difficult to detect because they're composed primarily of old, dim stars spread out over large volumes of space. Some dwarf galaxies in the local group contain fewer than 1 million stars, less than what you'd find in a single large globular cluster. They're more like loose associations of stars than proper galaxies, but they're gravitationally bound and count as separate structures. The Milky Way has more than a dozen confirmed satellite galaxies orbiting it, and new ones continue to be discovered as our telescopes and detection techniques improve. Some of these satellites are slowly being torn apart by the Milky Way's tidal forces, leaving streams of stars that trace out the satellite's orbital path. The Sagittarius dwarf elliptical galaxy, for example, is currently merging with the Milky Way, and its stars are being spread out into long tidal tails that wrap around our galaxy. In a few billion years, these stars will be fully incorporated into the Milky Way's halo, and the Sagittarius dwarf will cease to exist as a separate entity. The Large and Small Magellanic Clouds, visible as fuzzy patches in the southern sky, are irregular dwarf galaxies and two of the Milky Way's most prominent satellites. They're close enough and bright enough that they've been known to humans for thousands of years, described in the astronomical traditions of various southern hemisphere cultures long before European explorers documented them. These galaxies are being gravitationally harassed by the Milky Way, with streams of gas called the Magellanic Stream and the leading arm being pulled from them and eventually falling into our galaxy, fueling future generations of star formation. The local group as a whole is being influenced by much larger gravitational structures around it. The Virgo supercluster, which contains our local group along with thousands of other galaxies, has its own gravitational dynamics. Everything in our cosmic neighborhood is being pulled toward a mysterious region known as the Great Attractor, a gravitational anomaly located beyond the Virgo cluster. The Great Attractor itself is part of an even larger structure called the Laniakea supercluster, but we'll explore those cosmic structures in more depth later. What's peaceful and comforting about the local group is the realization that galaxies aren't isolated islands drifting alone through empty space. They exist in communities interacting with each other, sometimes colliding and merging, sometimes simply passing nearby and exchanging small amounts of material. These interactions happen slowly, over hundreds of millions or billions of years, timescales so long that they make human history seem like the briefest flicker. Galaxies are social creatures in their own way, bound together by gravity into families and groups that evolve together over cosmic time. Types and shapes of galaxies. As we pull back our view to look at galaxies beyond the local group, we begin to notice something remarkable. Galaxies come in a wide variety of shapes and sizes, each one unique but falling into recognizable categories. Understanding these types helps us see patterns in how galaxies form and evolve, how they respond to their environments, and how they change over cosmic time. The most familiar and visually striking galaxies are the spirals, those majestic pinwheel structures that grace many astronomy photographs. Spiral galaxies, like our Milky Way and Andromeda, consist of a flattened disk of stars orbiting around a central bulge. The disk contains spiral arms, regions of enhanced star formation that wind outward from the center. These arms are traced by bright blue stars and glowing pink nebulae, regions where gas clouds are actively collapsing to form new stellar generations. The spiral pattern is maintained by density waves that rotate through the disk, temporarily concentrating stars and gas into the visible arm structures. Spiral galaxies can be further divided into two main subtypes. Regular spirals have multiple spiral arms that emerge directly from the central bulge, creating a classic pinwheel appearance. Barred spirals, which appear to be the majority of spiral galaxies including our own Milky Way, have an elongated bar of stars running through their center, with the spiral arms beginning at the ends of the bar rather than emerging from the bulge itself. The bar is thought to form from instabilities in the disk, and it plays an important role in funneling gas toward the galaxy's center, potentially feeding the central supermassive black hole and triggering star formation in the central regions. Within these categories, spirals are further classified by how tightly their arms are wound, how large their central bulge is, and how much of their light comes from the arms versus the bulge. Galaxies with tightly wound arms and large bulges are classified as early-type spirals, while those with loose, open arms and small bulges are late-type spirals. These terms, early and late, don't actually refer to the age of the galaxies or their stage of evolution. They're historical terms from when astronomers thought they might represent an evolutionary sequence, which we now know isn't the case. Spiral galaxies are bright and beautiful, and they represent the most active star-forming galaxies in the nearby universe. The presence of substantial amounts of gas and dust in their disks provides the raw material for ongoing star formation, which is why spirals often appear blue in color photographs. That blue comes from the light of massive, young stars that burn hot and bright but live for only a few million years before exploding as supernovae. These galaxies are dynamic, living systems where the cycle of stellar birth and death continues to unfold. On the other end of the galactic spectrum are elliptical galaxies, which look entirely different from spirals. Elliptical galaxies lack the disk and spiral arm structure entirely. Instead, they're roughly spherical or ellipsoidal in shape, like cosmic footballs or soccer balls. They range from nearly perfect spheres to highly elongated ellipsoids, and astronomers classify them by their apparent degree of elongation, from E0 for nearly round galaxies to E7 for the most elongated ones. Elliptical galaxies come in a huge range of sizes. The smallest, called dwarf ellipticals, contain only a few million stars and can be fainter than a single bright star in our galaxy. The largest, called giant ellipticals or sometimes supergiant ellipticals, can contain trillions of stars and span several 100,000 light-years across. These giant ellipticals are typically found at the centers of large galaxy clusters, where they've grown to enormous sizes by cannibalizing smaller galaxies that wandered too close. The most distinctive feature of elliptical galaxies, aside from their shape, is their color. Most elliptical galaxies appear yellowish or reddish, reflecting the light of old, cool stars. Unlike spirals, ellipticals contain very little gas and dust, which means they have little ongoing star formation. The stars in elliptical galaxies are generally old, having formed billions of years ago when the galaxy was young and still had substantial gas reserves. Once that gas was used up or lost, star formation largely ceased, leaving behind populations of stars that have been gradually dimming and reddening as they age. Current theory suggests that many elliptical galaxies formed through the merger of two or more spiral galaxies. When spiral galaxies collide, their organized disk structures are disrupted. The orderly rotation of stars in the disk is converted into more random, chaotic motions. The collision can trigger intense bursts of star formation that rapidly consume the available gas. Over time, the merged system settles into an ellipsoidal shape, the combined mass of the original galaxies now moving in a more spherical arrangement. This merger origin explains why ellipticals often show evidence of past violence in their structure, and why they're more common in dense galaxy clusters where collisions happen more frequently. Between spirals and ellipticals lies an interesting intermediate class called lenticular galaxies, designated S0. Lenticular galaxies have a disk like spiral galaxies and a prominent central bulge, but they lack spiral arms. They appear smooth and featureless in photographs, without the bright arms and star-forming regions that characterize spirals. Like ellipticals, lenticulars have little ongoing star formation and are dominated by older stellar populations. They might represent a transition state between spirals and ellipticals, perhaps spirals that have had their gas stripped away or exhausted, or they might form through different processes entirely. Then there are the irregular galaxies, which, as their name suggests, don't fit neatly into the spiral or elliptical categories. Irregular galaxies lack any clear structure or symmetry. They appear as chaotic collections of stars, gas, and dust, often with multiple bright knots of star formation scattered throughout. Most irregular galaxies are small, containing only a few billion stars, though some can be quite massive. The shapes of irregular galaxies often result from gravitational interactions with other galaxies. A close encounter can distort a galaxy's structure, pulling it into strange shapes and triggering bursts of star formation where gas clouds collide. Some irregulars might be young galaxies that haven't yet settled into more organized structures, while others are clearly the victims of recent collisions or tidal interactions. The Large and Small Magellanic Clouds, the Milky Way's satellite galaxies, are examples of irregular galaxies that have been pulled into their current shapes by interactions with our galaxy's gravity. Beyond these basic types, there are various peculiar galaxies that defy easy classification. Ring galaxies, which have a ring-like structure of stars surrounding a relatively empty core, might form when a smaller galaxy passes directly through the disk of a larger galaxy, creating a ripple effect that propagates outward. Galaxies with multiple nuclei are often seen in the midst of mergers, where two galactic cores haven't yet merged but orbit within the same outer envelope of stars. Some galaxies show long tidal tails streaming away from them, scars from past encounters with other galaxies. The reason galaxies have these different shapes relates to their formation history and environment. A galaxy that forms in isolation, far from neighbors, can settle into a quiet spiral structure and maintain it for billions of years. A galaxy that forms in a dense cluster, constantly buffeted by the gravity of neighbors and sometimes colliding with them, will likely end up as an elliptical. The gas in a galaxy can be stripped away by interactions with hot gas in a cluster or consumed in bursts of star formation during mergers, affecting whether the galaxy can maintain an active spiral structure or must settle into the quiescent elliptical form. What's remarkable is that we can see all these types of galaxies scattered throughout the universe, frozen at different moments in cosmic history. Nearby galaxies show us what the local universe looks like now, while more distant galaxies, observed as they appeared billions of years ago, show us what galaxies looked like in the past. By studying galaxies at different distances and therefore different cosmic times, astronomers can piece together how galaxies evolve, how their shapes change, and how the balance between spirals and ellipticals has shifted over the history of the universe. The deep universe, beyond our neighborhood. Now let's expand our view even further, beyond the local group and into the deep universe where galaxies gather in even larger structures that stretch across hundreds of millions of light-years of space. This is where we encounter the cosmic web, the largest known structure in the universe, a pattern that reveals how matter organized itself in the aftermath of the Big Bang. Galaxies don't simply float randomly through space. They're drawn together by gravity into clusters, which are in turn organized into even larger structures called superclusters. These superclusters are arranged in filaments and sheets that surround vast, relatively empty regions called voids. The result is a structure that, when mapped out, looks remarkably like a three-dimensional spider's web or the neural network of a brain, with dense nodes connected by filaments and separated by empty spaces. The closest major cluster to us is the Virgo cluster, located about 54 million light-years away. This cluster contains more than 2,000 galaxies packed into a region about 15 million light-years across. At the center of the Virgo cluster sits a giant elliptical galaxy called Messier 87, or M87, which gained fame in 2019 when the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. Specifically, the shadow of the supermassive black hole at M87's center, which has a mass of 6.5 billion times the mass of our Sun. The Virgo cluster exerts a gravitational pull on our local group, drawing us toward it at a speed of several hundred kilometers per second. This motion toward Virgo is superimposed on the general expansion of space, creating a complex pattern of motion where we're simultaneously being carried away from distant galaxies by the expansion of space while being pulled toward nearby massive structures by gravity. But the Virgo cluster itself is part of something even larger. The Virgo supercluster, a collection of galaxy clusters and groups spanning roughly 110 million light-years. Our local group sits on the outskirts of this supercluster, in a relatively sparse region. The Virgo supercluster contains approximately 47,000 galaxies, though this number is approximate and depends on exactly where you draw the boundaries of the supercluster. For many years, astronomers thought the Virgo supercluster represented one of the largest structures in the universe. Then, in 2014, a team of astronomers led by Brent Tully announced the discovery of an even larger structure that contains the Virgo supercluster as just one component among several. They called this enormous structure Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster of superclusters, defined not by the visible distribution of galaxies but by the pattern of motion of galaxies through space. Using careful measurements of how galaxies are moving, Tully and his colleagues identified a region where all the galaxies are flowing inward toward a common gravitational center. This region, Laniakea, contains approximately 100,000 galaxies spread across 520 million light-years. The mass of all these galaxies combined amounts to about 100 quadrillion times the mass of the Sun. The discovery of Laniakea helped clarify some puzzles about galactic motion. Astronomers had known for decades that our local group and other nearby galaxies were being pulled toward a mysterious region called the Great Attractor, located in the direction of the constellation Centaurus. The Great Attractor isn't a single object but rather a region of high galaxy concentration, and it turns out to be just one part of an even larger concentration of mass at the center of Laniakea. All the galaxies in Laniakea are slowly flowing toward this central region, drawn by its immense gravitational pull. Laniakea isn't alone. It has neighbors, other superclusters with names like Perseus Pisces, Coma, and Shapley. These structures are arranged in the cosmic web, forming the filaments and nodes that make up the large-scale structure of the universe. Between the filaments lie the voids, enormous regions of space that contain very few galaxies. These voids aren't completely empty. They contain some galaxies and dark matter, but they're vastly underdense compared to the filaments and clusters. The cosmic web structure has its origins in the very early universe, shortly after the Big Bang. In the first few 100,000 years of cosmic history, matter and energy were distributed almost, but not quite, uniformly. There were tiny fluctuations in density, regions that were slightly denser than average and regions that were slightly less dense. These fluctuations, imprinted during the first fraction of a second after the Big Bang by quantum processes we still don't fully understand, were the seeds that would grow into all the structure we see today. As the universe expanded and cooled, gravity amplified these initial density fluctuations. Regions that were slightly denser than average exerted a slightly stronger gravitational pull, attracting nearby matter. This made them even denser, which strengthened their gravity further, which attracted more matter. Meanwhile, regions that started out slightly less dense than average lost matter to the denser regions, becoming even emptier. Over hundreds of millions of years, this process transformed the nearly uniform early universe into the clumpy cosmic web we observe today. The first structures to form were relatively small, comparable in size to present-day dwarf galaxies. These initial galaxies then merged and assembled into larger galaxies, which continued to merge into even larger systems. This hierarchical assembly process is still ongoing today. We see evidence of it in the satellite galaxies orbiting the Milky Way, in the ongoing collision between Andromeda and Triangulum, and in the massive elliptical galaxies in cluster centers that have grown huge by consuming their neighbors. The pattern of the cosmic web encodes information about the fundamental properties of the universe. By studying the statistical properties of galaxy clustering, the sizes of voids, and the masses of galaxy clusters, astronomers can constrain models of cosmic evolution and measure parameters like the amount of dark matter, the strength of dark energy, and the rate of cosmic expansion. The web is, in essence, a fossil record of the early universe, a pattern frozen into the distribution of matter that tells the story of everything that has happened since the Big Bang. When we look at the deep universe, observing galaxies billions of light years away, we're seeing this cosmic web at different stages of its evolution. Nearby, the web is well defined with clear filaments and voids. At greater distances, looking back to times when the universe was younger, the structure is less pronounced. The filaments are thinner, the voids smaller, the clusters less massive. If we could look back far enough, we'd see a time before any structure formed at all, when the universe was truly uniform aside from those tiny quantum fluctuations that started everything. One of the most distant structures yet discovered is a protocluster of galaxies observed at a distance of about 12.9 billion light-years, meaning we're seeing it as it appeared when the universe was less than 1 billion years old. At that time, this protocluster was a loose association of 14 galaxies in the process of forming what would eventually become a massive galaxy cluster. Over the billions of years since that light left, those galaxies have merged and assembled into a much more compact structure, similar to the massive clusters we see in the nearby universe. The scale of the cosmic web is humbling. The filaments extend across hundreds of millions of light-years. The voids between them can be 200 million light-years or more across. If you could somehow cross one of these voids at the speed of light, it would take you 200 million years to reach the other side, during which time you'd encounter very few galaxies. The voids are monuments to emptiness, vast regions where the darkness between galaxies stretches on and on, with only occasional dim dwarf galaxies breaking the void. And yet, even these enormous structures are dwarfed by the size of the observable universe itself. Laniakea, as vast as it is, represents only a tiny fraction of the cosmos we can see with our telescopes. There are countless other superclusters scattered throughout the observable universe, each one containing tens of thousands of galaxies, each galaxy containing billions of stars. The number of stars in the observable universe has been estimated at around 200 billion trillion, a 2 followed by 23 zeros. That's more stars than grains of sand on all the beaches on Earth. Understanding this cosmic hierarchy, from planets to solar systems to galaxies to groups to clusters to superclusters to the cosmic web itself, gives us a sense of perspective that's simultaneously humbling and empowering. We occupy a particular place in this hierarchy, tiny beyond measure yet connected to everything else through the same physical laws, the same gravitational forces, the same cosmic history. We're made of atoms forged in the cores of stars, stars that formed from gas clouds in galaxies, galaxies that coalesced from the primordial density fluctuations in the early universe. Our existence is intertwined with the largest structures in the cosmos. Ancient light and looking back in time. One of the most profound aspects of observing distant galaxies is that we're not seeing them as they are now, but as they were in the distant past. This isn't a limitation of our telescopes. It's a fundamental consequence of the finite speed of light and the vast distances involved in cosmic scales. Understanding this temporal dimension of astronomy transforms our view of the universe from a static snapshot into a dynamic story unfolding across billions of years. Light travels at approximately 300,000 kilometers per second, which seems instantaneous on human scales. The light from your phone screen reaches your eyes in less than a billionth of a second. Light from the sun takes about 8 minutes to reach Earth, which means we see the sun as it was 8 minutes ago. If the sun were to suddenly vanish, we wouldn't know about it for 8 minutes. We'd continue to see it shining in the sky until that last bit of light reached us. This time delay becomes more and more significant as we look at more distant objects. The light from the nearest star beyond the sun, Proxima Centauri, takes about 4 years to reach us. The light from the center of our galaxy takes 26,000 years. The light from the Andromeda Galaxy takes 2.5 million years. And when we look at the most distant galaxies, we're seeing light that has been traveling through space for more than 13 billion years, nearly the entire age of the universe itself. This means that our telescopes are effectively time machines. When we observe a galaxy 10 billion light-years away, we're seeing that galaxy as it appeared 10 billion years ago, when the universe was less than a quarter of its present age. The galaxy surely still exists somewhere out there in space, but we can't see what it looks like now. The light showing us its current appearance won't reach Earth for another 10 billion years, by which time the sun will have long since died and Earth will be gone. This ability to look back in time is an incredibly powerful tool for understanding cosmic history. By observing galaxies at different distances, we're effectively observing galaxies at different ages, allowing us to watch how galaxies evolve over time. We can compare galaxies in the nearby universe, which appear as they did relatively recently, to galaxies in the distant universe, which appear as they did in the ancient past, and see how galaxy properties change over cosmic time. One striking observation is that galaxies in the early universe look different from nearby galaxies. Early galaxies tend to be smaller, more irregular in shape, and often show intense bursts of star formation. They're building themselves up through mergers and accretion, assembling mass piece by piece. The well-ordered spiral galaxies we see nearby took billions of years to develop. In the early universe, most galaxies were scrappier, more chaotic, still in the process of formation. The most distant galaxies we can currently observe are seen as they appeared less than a billion years after the Big Bang. These ancient galaxies were detected by the James Webb Space Telescope, which launched in 2021 and began science operations in 2022. Thanks to its unprecedented sensitivity and its ability to observe in infrared wavelengths, JWST can detect galaxies so distant that their light has been traveling through space for more than 13 billion years. What's remarkable is that some of these ancient galaxies appear surprisingly mature and massive. Before JWST, many astronomers expected the earliest galaxies to be small, messy collections of stars. But JWST has found galaxies from less than 500 million years after the Big Bang that already contain billions of stars and show signs of organized structure. These observations are challenging our understanding of how quickly galaxies could form in the early universe and may require adjustments to our models of galaxy evolution. The light from these ancient galaxies has been transformed during its journey to us. The expansion of space has stretched the wavelengths of the light, shifting it toward the red end of the spectrum in a phenomenon called cosmological redshift. Light that was emitted as ultraviolet or visible light has been redshifted into the infrared by the time it reaches us. This is why infrared telescopes like JWST are essential for studying the most distant galaxies. Their light has been shifted out of the visible range entirely. There's a practical limit to how far back we can see with light. the universe wasn't transparent in its earliest stages. For the first 380,000 years after the Big Bang, the universe was so hot and dense that it was opaque, filled with a plasma of electrons and atomic nuclei that scattered light in all directions. Only after the universe expanded and cooled enough for electrons and nuclei to combine into neutral atoms did space become transparent. This era, called recombination, marked the moment when light could finally travel freely through space. The light released at that moment is still traveling through space today, stretched by the universe's expansion into microwaves. This is the cosmic microwave background, or CMB, the oldest light in the universe. The CMB appears to come from all directions in the sky, a faint glow with a temperature of about 2.7 degrees above absolute zero. Detailed maps of the CMB, made by spacecraft like the Planck telescope, show tiny variations in temperature across the sky. These variations represent the density fluctuations that would eventually grow into all the structure we see today: galaxies, clusters, superclusters, the entire cosmic web. Before recombination, before the CMB was emitted, we can't see anything with light because the universe was opaque. This represents a fundamental horizon in our observations of cosmic history. We can use other techniques like detecting gravitational waves or looking for relic neutrinos to probe earlier times, but we can never directly observe light from before the CMB. The first 380,000 years of cosmic history are hidden from us behind this wall of opacity. But between the CMB and the present day, we have a remarkably complete record preserved in light. Galaxies at different distances provide snapshots from different eras. By carefully studying these cosmic fossils, astronomers have pieced together the story of how the universe evolved from a nearly smooth, hot plasma to the complex, structured cosmos we see today. We can trace the formation of the first stars, the assembly of the first galaxies, the era when most stars were forming called cosmic noon occurring about 10 billion years ago, and the gradual settling of the modern universe into its current state. Looking at these distant galaxies, seeing light that has been traveling for billions of years, there's a profound sense of connection to deep time. The photons entering your eye or hitting a telescope's detector tonight left their source galaxy when the universe was young, before our solar system existed, before the Milky Way had taken its current form. These photons have crossed half the universe or more, threading their way through expanding space, surviving the journey intact, to finally arrive here and tell us their story. Every distant galaxy is a message from the past, and we're privileged to be able to decode it. The mystery and beauty of dark matter. As we explore the cosmos, one of the most profound mysteries we encounter is the realization that most of the matter in the universe is invisible. The stars, gas, dust, and planets we can see directly make up less than a sixth of all the matter that exists. The rest is something called dark matter, which doesn't emit, absorb, or reflect light. We can't see it directly, but we know it's there because of its gravitational effects on visible matter. Understanding dark matter is crucial to understanding how galaxies form, hold together, and evolve over time. The first hints of dark matter came from observations in the 1930s, when astronomer Fritz Zwicky studied the motion of galaxies in the Coma cluster. He noticed that the galaxies were moving much faster than they should be, given the amount of visible mass in the cluster. According to the laws of gravity, the galaxies should be moving fast enough to escape the cluster's gravitational pull, yet they remained bound together. Zwicky proposed that the cluster must contain large amounts of unseen matter, providing additional gravity to hold everything together. He called this unseen matter dunkle materie, or dark matter. For decades, Zwicky's observations were largely ignored or considered inconclusive. Then, in the 1970s, astronomer Vera Rubin conducted detailed studies of how spiral galaxies rotate. She measured the speed of stars and gas clouds at various distances from the centers of galaxies, expecting to find that objects farther from the center would orbit more slowly, just as outer planets in our solar system orbit more slowly than inner planets. Instead, she found that rotation speeds remained roughly constant or even increased with distance from the galactic center. This implied that galaxies must contain far more mass than we can see, distributed in a large halo extending well beyond the visible edge of the galaxy. These dark matter halos appear to be essential to galaxy formation and structure. Computer simulations of galaxy formation show that without dark matter, gas clouds in the early universe wouldn't have had enough gravity to collapse and form galaxies. The dark matter acts as a gravitational scaffolding, creating potential wells into which normal matter can fall. Once a concentration of dark matter forms, it attracts gas, which cools and condenses, eventually forming stars. The visible galaxy we see is essentially the bright center of a much larger, invisible structure. The distribution of dark matter in and around galaxies has been mapped using several techniques. One of the most striking is gravitational lensing, which occurs when light from a distant background galaxy passes near a massive foreground object like a galaxy cluster. The gravity of the foreground object bends the light, acting like a lens and distorting the image of the background galaxy. By studying these distortions, astronomers can map out the distribution of mass in the foreground object, including both visible and dark matter. Some of the most dramatic examples of gravitational lensing come from observations of galaxy clusters. The Hubble Space Telescope has captured images of clusters where the combined mass of hundreds of galaxies, plus their dark matter halos, creates a powerful gravitational lens. Background galaxies appear stretched into arcs or even complete rings called Einstein rings. By analyzing these distorted images, astronomers can create maps showing where the dark matter is concentrated. These maps often show that the dark matter is distributed in smooth, approximately spherical halos centered on the cluster, with the visible galaxies embedded within this larger dark matter structure. One of the most compelling pieces of evidence for dark matter comes from observations of the Bullet Cluster, a system where two galaxy clusters have collided and passed through each other. When the clusters collided, the hot gas in each cluster interacted, slowed down, and became separated from the galaxies themselves. Gravitational lensing measurements show that most of the mass in the system didn't slow down. It passed right through with the galaxies. This separated mass is dark matter. The Bullet Cluster demonstrates that dark matter must be something other than ordinary matter in some difficult-to-detect form. It's something that interacts gravitationally but hardly at all through electromagnetic forces, allowing it to pass through other matter almost unimpeded. What dark matter actually is remains one of the biggest unsolved problems in physics. We know it's not made of ordinary atoms because if it were, it would interact with light and we'd be able to see it. Various candidates have been proposed. One possibility is that dark matter consists of exotic particles left over from the Big Bang, particles that interact only weakly with ordinary matter. Physicists have built sensitive detectors deep underground, shielded from cosmic rays and other background radiation, trying to catch the rare occasions when a dark matter particle might collide with an atomic nucleus. So far, these experiments haven't detected anything conclusive, but they've ruled out many possible models and are steadily narrowing down the properties that dark matter could have. Another possibility is that dark matter might be composed of primordial black holes that formed in the early universe from density fluctuations before stars ever existed. These would be gravitationally detectable but wouldn't emit any light. However, various astronomical observations have placed tight constraints on how many primordial black holes could exist, suggesting that while they might contribute to dark matter, they probably don't account for all of it. The mystery of dark matter extends beyond just figuring out what particles it's made of. We're also trying to understand how dark matter is distributed on different scales, from the smallest clumps to the largest structures in the cosmic web. Simulations suggest that dark matter should form a hierarchical structure, with small halos merging to form larger ones in a process that mirrors the assembly of visible galaxies. The smallest dark matter halos might contain no visible matter at all. They might be entirely dark, invisible structures that we can only detect through their gravitational effects. The distribution of dark matter throughout the universe shapes everything we see. The cosmic web of filaments and voids is primarily a dark matter structure. The visible galaxies are simply the bright regions where enough normal matter collected to form stars. If we could somehow view the universe in dark matter light, we'd see an intricate network of filaments and halos, with the visible galaxies appearing as small bright kernels at the densest nodes. Understanding dark matter has profound implications for our view of cosmic history. The balance between dark matter, normal matter, and dark energy determines how fast the universe expands, how quickly structures form, and what the ultimate fate of the cosmos will be. Detailed measurements of galaxy clustering, gravitational lensing, and the cosmic microwave background have allowed astronomers to measure the amount of dark matter in the universe quite precisely. It makes up approximately 27% of the total mass energy content of the universe, compared to about 5% for normal matter and 68% for dark energy. What's peaceful about contemplating dark matter is recognizing that the universe contains far more than we can directly perceive. There are entire layers of reality that exist beyond our immediate senses, structures and patterns that reveal themselves only through careful observation and mathematical analysis. The universe is deeper and stranger than it appears on the surface, and our growing understanding of phenomena like dark matter shows how far human intellect can reach, unveiling secrets that remain hidden to casual observation. Life cycles, galaxy birth, evolution, and death. Galaxies, despite their vast size and seemingly eternal nature, have life cycles of their own. They're born, they evolve, they interact with their environment and with other galaxies, and eventually they die, though the death of a galaxy is a much more ambiguous concept than the death of a star. Understanding these life cycles helps us see galaxies not as static objects but as dynamic systems changing over billions of years, shaped by both internal processes and external influences. The story of galaxy formation begins in the early universe, in the first few 100 million years after the Big Bang. At this time, the universe was filled with primordial gas, mostly hydrogen and helium created during the first 3 minutes of the Big Bang. This gas wasn't quite uniformly distributed. There were slight density fluctuations, tiny quantum ripples from the inflationary epoch that had been stretched to cosmic scales. Where the gas was slightly denser, gravity pulled in more gas, making these regions even denser. This process of gravitational instability, amplified over millions of years, eventually created the first large-scale structures. The earliest objects to form were probably quite small, with masses perhaps 1,000,000 times the mass of the Sun. These were regions where gas had become dense enough to cool and collapse, triggering the formation of the first stars. These initial stars were very different from stars forming today. The primordial gas contained no heavy elements, only hydrogen and helium, which meant it had to cool through different processes than modern gas clouds. The first stars are thought to have been extremely massive, perhaps hundreds of times the mass of the Sun, burning bright and hot but living for only a few million years before exploding as supernovae or collapsing directly into black holes. These early stellar systems, too small and short-lived to really count as galaxies, began merging together. Larger structures formed through the merger of smaller ones, a process called hierarchical assembly that continues to this day. As these proto-galaxies grew, they pulled in more gas from their surroundings, triggering more star formation. The stars that formed began producing heavy elements through nuclear fusion, and when massive stars exploded as supernovae, they scattered these elements into space, enriching the surrounding gas. Subsequent generations of stars formed from this enriched gas, gradually changing the chemical composition of galaxies from the pure hydrogen and helium of the early universe to the complex mix of elements we see today. The process of galaxy formation is turbulent and chaotic. Early galaxies were constantly buffeted by mergers, both with other small protogalaxies and with streams of gas falling in from the cosmic web. Star formation rates in early galaxies were often very high, with massive amounts of gas being converted into stars over relatively short periods. This era of intense activity, occurring roughly 10 to 12 billion years ago, is sometimes called cosmic noon, because this is when the universe's overall star formation rate reached its peak. As galaxies grew and matured, different physical processes began to shape their evolution. For spiral galaxies like the Milky Way, a crucial development was the formation of a stable disk. Gas settling into the gravitational potential well of the dark matter halo tended to conserve angular momentum, causing it to flatten into a rotating disk. Within this disk, spiral density waves could form, organizing star formation into the spiral arms we see today. The disk continued to accrete gas from the surrounding halo and from smaller satellite galaxies, fueling ongoing star formation that continues into the present era. Elliptical galaxies, on the other hand, lost their organized disk structure through major mergers. When two spiral galaxies of roughly equal mass collide, the encounter is violent and transformative. The orderly rotation of the disks is disrupted, stars are flung onto new, more random orbits, and the gas is funneled toward the center where it triggers an intense starburst. The central supermassive black holes of both galaxies may also merge, releasing enormous amounts of energy as they spiral together. The end result, after several billion years of interaction and eventual merger, is an elliptical galaxy with no remaining disk structure. The centers of galaxies contain supermassive black holes, objects with masses ranging from millions to billions of times the Sun's mass. These black holes appear to co-evolve with their host galaxies. There's a tight relationship between the mass of a galaxy's central black hole and the mass of the galaxy's bulge, suggesting that processes in the galactic center influence galaxy evolution, and vice versa. When gas falls toward a supermassive black hole, It forms an accretion disk that heats up and emits enormous amounts of radiation. If the black hole is actively feeding, the galaxy becomes what astronomers call an active galactic nucleus, or AGN. The most extreme AGN are quasars, extraordinarily luminous objects that can outshine entire galaxies despite the light coming from a region no larger than our solar system. Quasars were much more common in the early universe than they are today, suggesting that galaxies went through active phases when their central black holes were rapidly accreting material. The energy released by these AGN can blow gas out of the galaxy entirely, shutting down star formation. This process, called AGN feedback, is thought to be one of the main mechanisms that stops large galaxies from forming too many stars too quickly. Over billions of years, galaxies can undergo multiple cycles of activity and quiescence. A galaxy might undergo a burst of star formation triggered by a merger, exhaust or expel its gas supply, enter a quiet period with little star formation, then later accrete new gas and experience another burst. The balance between gas inflow, star formation, supernovae and stellar winds pushing gas out, and AGN feedback blowing gas away determines how a galaxy evolves over time. Galaxies can also die in a sense by running out of gas and ceasing all star formation. This happens most commonly in dense galaxy clusters, where several processes can remove a galaxy's gas supply. Ram pressure stripping occurs when a galaxy moves through hot gas in the cluster, with the pressure of this hot gas pushing the cooler gas out of the galaxy like wind blowing leaves off a tree. Tidal stripping occurs when close encounters with other galaxies or with the cluster's gravitational field pull gas away from a galaxy. Strangulation occurs when the hot gas surrounding a galaxy is removed, cutting off the supply of cooling gas that would normally replenish the galaxy's star-forming regions. Once a galaxy runs out of gas, it can no longer form new stars. Existing stars continue shining, but over time the most massive and luminous stars die, leaving behind only long-lived, dim stars. The galaxy gradually fades, becoming redder as the hot blue stars disappear, and only cool red and yellow stars remain. This process can take many billions of years, but eventually the galaxy becomes what astronomers call red and dead, an elliptical or lenticular galaxy with no ongoing star formation, dominated by old stellar populations. However, a dead galaxy can potentially be revived if it acquires new gas, either by accreting a gas-rich satellite galaxy or by moving into an environment where fresh gas is available. Some elliptical galaxies show evidence of recent or ongoing star formation, suggesting they've somehow acquired new fuel. The life cycle of galaxies is not necessarily a one-way progression from birth to death, but rather a complex story with possible loops, reversals, and second acts. In the very long-term future, trillions of years from now, galaxy evolution will enter entirely new phases. The universe's expansion will have carried distant galaxies beyond the horizon, leaving only the gravitationally bound galaxies of the local group. These galaxies will likely merge into a single massive elliptical. Star formation will eventually cease throughout the universe as the gas supply is exhausted. Stars will age and die one by one until only the longest-lived red dwarfs remain, stars that can burn for trillions of years. Eventually, even these will fade, leaving behind dead stellar remnants. White dwarfs, neutron stars, and black holes in an increasingly dark and empty cosmos. The eternal cosmos. As our journey through the realm of galaxies comes to a close, Take a moment to let everything settle in your mind. Think about the vastness we've explored together, from the familiar spiral of the Milky Way to the incomprehensible scale of superclusters stretching across hundreds of millions of light-years. Think about the ancient light that has traveled for billions of years to reach our telescopes, carrying messages from a younger universe. Think about the invisible dark matter scaffolding that holds everything together, the gentle dance of galaxies through space, the birth and death of stellar generations within those galaxies. There's something deeply comforting about the universe's immensity and its age. The galaxies we've discussed tonight have been spinning through space for billions of years, long before Earth formed, long before life began, long before humans emerged to wonder about the stars. They'll continue spinning for billions of years after we're gone, following their appointed paths through space, governed by the same laws of physics that have guided them since the beginning. This continuity, this vast, unchanging rhythm of cosmic evolution, offers a kind of perspective that's difficult to find in our daily lives. Your worries, your concerns, the things that keep you up at night, all real and valid and important to you. But they're also temporary, bound to this moment, this place, this infinitesimally brief span of cosmic time. The galaxies know nothing of human troubles. They continue their slow waltz through the universe, indifferent to our existence, following paths determined billions of years ago. There's freedom in recognizing this, a release from the weight of believing that everything depends on us, that every problem is urgent, that every mistake is permanent. At the same time, the fact that we can understand galaxies, that we can measure their distances, decode their light, reconstruct their histories, and predict their futures is remarkable. We're made of stardust. Literally, the atoms in our bodies were forged in the cores of long-dead stars, stars that lived and died within galaxies much like the Milky Way. We're a way for the universe to know itself, to understand its own structure and history. We're stardust contemplating stars, and there's a poetry to that which transcends the cold mathematical language of astronomy. As you drift towards sleep, imagine yourself floating peacefully in the space between galaxies, suspended in the gentle darkness. Above you, below you, all around you, islands of stars shine with their soft, ancient light. Some are spirals with their elegant arms. Some are smooth ellipticals glowing with the light of 1 trillion suns. Some are irregular and chaotic, still forming, still changing. They're all beautiful in their own way, each one a unique collection of stars and worlds, each one with its own history, its own story to tell. You're connected to all of it through the most fundamental forces in nature. Gravity links you to every other piece of matter in the universe, from the smallest atom to the largest supercluster. The electromagnetic forces binding atoms together in your body are the same forces that make stars shine and galaxies glow. The atoms that make up your body, your brain, your thoughts, were created in the hearts of stars billions of years ago. You are not separate from the cosmos but a part of it, a brief pattern of consciousness that emerged from the universal dance of matter and energy. Let yourself relax completely now. Feel the weight of your body sinking into rest. Let your breathing slow and deepen. There's nowhere you need to be, nothing you need to do. The universe will continue its slow unfold whether you're watching or not. Galaxies will continue spinning. Stars will continue shining. The cosmic web will continue its gentle evolution across billion-year timescales. All of this will go on, patient and eternal and beautiful, while you rest. Tomorrow you'll wake to a new day, but the galaxies we've discussed tonight will still be there, invisible during the day but present nonetheless, continuing their ancient journeys through space. The Milky Way will still be carrying us around its center at 200 kilometers per second. Andromeda will be slightly closer than it was today, approaching for its eventual merger billions of years hence. The cosmic web will continue its slow evolution, clusters growing denser while voids grow emptier. The universe will be fractionally older, fractionally larger, still expanding into the infinite future. Before you fully let go into sleep, consider one last thought. Somewhere out there, in another galaxy far across the universe, there might be someone else looking up at their own night sky, seeing their own view of the cosmic tapestry, perhaps wondering if they're alone, perhaps contemplating the same questions we contemplate. The universe is vast enough to contain countless stories, countless perspectives, countless ways of experiencing existence. We're one tiny part of that vast multiplicity, one brief spark of consciousness in an ocean of space and time. Rest now. Let the peace of cosmic scales wash over you. Let the gentle spinning of galaxies lull you into sleep. You are small, but you are part of something unimaginably vast and ancient and beautiful. You are stardust, you are cosmic, you are a temporary pattern in an eternal dance. If you're enjoying this gentle journey through the galaxy and finding yourself feeling calmer and more relaxed, you can softly tap the like button to support the video. And if you'd like more peaceful science stories like this exploring space, the universe, and the wonders of nature, consider subscribing to Deep Science Sleep. Your support helps this channel continue creating slow, soothing documentaries designed to help you unwind, let go of the day, and drift peacefully into sleep. New relaxing science videos are added regularly, always with a calm voice, gentle pacing, and a focus on rest. Thank you for being here, and now, let's continue floating quietly through the stars.